We're now ready to look at the field inside the outer conductor. So this is going to be the path inside here. And we're going to make it also a function of capital R. So let's write up our formula for Ampere's law. So we have the contour integral b vector dot dl vector is equal to mu naught times I enclosed. So this is just going to be b times 2 pi r for my distance around is equal to mu naught. And now I enclosed is going to have two parts. First, I have the inner conductor, which is completely inside. So that's going to be I naught. And then I'm going to have just this section of the outer conductor. So I'm going to have minus, because it's going in the opposite direction, because the outer conductor, the currents go in the opposite direction. I'm going to have J outer times this area, which is going to be pi, and then I want from R to R2, so it's going to be R squared minus R2 squared. And that's my total enclosed charge. Now I can take and solve for B. Two pi r. And notice that I can now substitute in for my J outer, and that's going to be minus I naught, and then I'm going to have pi r squared minus r2 squared over pi times r3 squared minus r2 squared. Now the i's can come out, I naughts. And that leaves me with 1 minus, the pi's are going to go away, so I'm going to have r squared minus r2 squared over r3 squared minus r2 squared. And now this can be simplified even more. And that's if I make this 1 equal to r cubed squared minus r2 squared over r3 squared minus r2 squared. That gives me a common denominator. And notice that I'm going to have a minus r2 squared minus a minus r2 squared, so the r2 squareds are going to go away, and it's going to leave me with mu naught I naught over 2 pi r times the quantity r3 squared minus r squared over r3 squared minus r2 squared. Now this is interesting because here I have an r squared, and in the denominator I have an r, and so in effect those are going to basically kind of cancel each other out. Even though I've got this other stuff going on with it, it's going to make that term fairly linear, and it's in the negative direction. So now we can take and plot a plot showing the inner radius of of 1 centimeter for the conductor, and then from 1 centimeter to 2 centimeters is empty space, and from 2 centimeters to 2.5 centimeters is a conductor, and then 2.5 on out is the outside of the coax. So you notice that the first section is linear. The second section dies out by 1 over r. Third section is linear in the negative direction, and the fourth segment is 0 because there's no magnetic field outside of the coaxial cable.